Okay, so to summarize this first section in chapter 6, which talks about how we find maximum likelihood estimates. So this involves calculus and algebra. So the previous videos, as you saw, used quite a bit of calculus and algebra. So be sure you brush up on those skills. But some observations that we've made in these examples, we looked at one example where we had a binomial distribution and we didn't know what the parameter p was. And so we found the probability of getting our observed sample, and then we found the value of p that made that most likely. And what we found was that value for p is p hat. Okay, so what we found was that the actual maximum likelihood estimate for p was equal to the sample proportion of successes. So we just would have been equivalent to saying how many total successes did we get out of how many total trials out of all of the samples. So that makes sense that the value of p that's going to make our observed output most likely is going to be to use the proportion from our observed output. So it's nice when our estimates make sense. And we could do the same for the exponential. We did the same for the exponential distribution. And in that case, we found that this parameter lambda was equal to 1 over the sample mean. And that also is a nice result because in general, this value lambda is equal to 1 over the expected value of x. So we're getting results that make sense. And that's always good property to have for an estimator. And so one last theorem that I'm not going to go through here because the book does a very good job of proving this. So I would definitely encourage you to take a look at theorem 6.1.3 from the textbook. And they go through the maximum likelihood estimates for the mean and standard deviation for a normal distribution. And they similarly find that the maximum likelihood estimate for mu is actually the sample mean. And the maximum likelihood estimate for sigma is what we would get if we were to calculate this value over here, which is pretty close to what the definition of sigma is. And so one thing to note here is with normal distributions, they depend on two parameters. So when you find your likelihood function, that's going to be a function of two variables. It's going to be a function of the parameter mu and the parameter sigma. So when you go through that process, it actually is going to require you the same calculus that's required to find the maximum value for a function of two variables. So there's going to be some multivariable calculus in that, but it's worth going through and reading and just verifying for yourself how we can get the estimates for mu and for sigma. I wouldn't ask you guys to prove that, but I think it's worth convincing yourself. So to kind of summarize here is that the maximum likelihood estimates, they give reasonable estimates that make sense. And that's always a great quality to have. In the next section, 6.2, we'll take a look at another method that we can use called the method of moments to come up with estimates. And once we have these two methods developed, then we can talk about some general properties of estimators that we hope our estimates satisfy. But that will be it for this worksheet.